Hi everyone, my name is Kunal Sharma. I am pursuing BSc Honors Data Science and AI at IIT Guwahati. Today I am presenting my term project 2 for course DA 378 Data Preparation and Sentiment Classification. Let's begin. The main objective of this project was to design, pre-process, and train and optimize machine learning text classification pipeline. This pipeline automatically predict the emotional tone, either positive or negative, from unstructured customer review and text corpora. Key milestone accomplished in this project include ingesting and merging a dataset exceeding 90,000 multi-score review, implementing a clean text preprocessing pipeline using regular expression, extracting numerical feature using TF-IDF vectorization restriction to 30,000 features, training, evaluating, and serializing a tuned logistic regression classification model. Let's touch on the core challenges that motivated this work. Unstructured text exploration. Digital platforms generate millions of reviews daily. Manual inspection is impossible, making automated sentiment classification essential. Data noisiness. Raw textual data is inherently messy. It is filled with HTML tags, slangs, emojis, and irregular formatting that degrade model performance if left uncleared. Vector space challenge. Text must be converted into high-dimensional numeric values, space efficiency while retaining semantic content. For dataset collection and integration, corpus merging I combined multiple standard public dataset including IMDb movie reviews and benchmark text corpora to form a unified training set of cover over 90,000 records. Class balance and an equal representative of positive and negative classes was ensured to prevent gradient optimization bias. The data consists of tabular row of pairing unstructured raw reviewed text with binary target label 0 for negative and 1 for positive. To transfer noisy raw data into clean input, I built a multi-stage pre-processing pipeline, HTML tag removal, regress pattern, machine stripped embedded markup noise, punctuation and noise cleanup, special character, numbers, and symbol were systematically removed. Case numeralization standardized all text lowercase via Python's dot lower, so word like great and great map to a single token. White space trimming, redundant space, and trailing character were stripped. Two key hyperparameter choice were critical here. Max feature capped at 30,000 top stump to contain sparse matrix memory uses, and gram configured to include both unigram and bigram, allowing the model to capture word combination and negation like not good. For feature extraction, I use term frequency inverse document TF-IDF weight word by balancing local frequency in a review against inverse frequency across the entire corpus, effectively downweighing common stop words. Moving on to the development. Model selection. Logistic regression uh, logistic regression was selected due to its linear decision boundary efficiency, low inference latency in text tasks. Regularization tuning, the inverse regularization parameter C was tuned to 2.0, striking an optimal balance between training fit and generalization. Serialization using job lab I serialized both the trained classification weight and the TF-IDF vectorized vocabulary into persistent binary file, unified model PKL for deployment. Here is the benchmark result across multiple algorithms. A baseline decision tree achieved 74% accuracy. Multinomial bias achieved 86.4%. Linear support vector classifier achieved a strong 91.1%. Our tuned unified logistic regression model outperformed the rest, achieving an overall accuracy of 92.5 with excellent stability across unseen validation splits. To guarantee reproducibility and deployment readiness, the project deliverables are structured into modular artifact, unified model.pkl, serialized binary containing the fitted logistic regression classification weight, unified vectorization PKL, serialized TF-IDF vocabulary transformation, train unified model.py, master execution script governing data injection, preprocessing, and model training, app.py, streamlit web application interface for real-time interference. Technic- uh, Technical learning. Reflecting on a key technical learning, data engineering, I gained a hands-on experience of mastering regular expression for noise removal, managing high-dimensional sparse metrics, and executing pipeline processing via JobLab. A practical insight, I developed a deeper understanding of trade-off between model complexity and interference speed and learning how linear model with quality n-gram feature can match or exceed heavier algorithm in text classification. Looking toward future improvement, transformer model, upgrading from back toward TF-IDF to fine-tuned contextual transformer architects like BERT or DistilBERT, cloud containerization, Dockerization, prediction endpoint for scalable enterprises deployment. Expect-based sentiment, expanding the binary sentiment classification into granular attribute level polarization. Thank you all.